Welcome to ALPHORES e-learning. So we are discussing about properties of ethers. In previous session we have completed that property of ethers with sulfuric acids and then hydrolysis reactions. Now in session 37 we will discuss the property of ether hydrogen halides, hydrohaloacids. Why? Because hydrohaloacids means these are not carrying any type of oxygen. That's why generally called what? Hydroacids. So hydrohaloacids means hydrogen with the halogen compounds like HCl, HBr, HI like this. So action of HI or reaction with HI, whatever one we can take here. So reaction with HX or action of hydrogen halogen compounds. X is equal to chlorine or bromine or iodine. Chlorine, bromine, iodine here. According to the stability order, hydrogen halides stability from top to bottom decreases due to increase in atomic size of iodine. So from top to bottom atomic size increases, then the bond length increases, the compound stability decreases, reactivity increases. That means if you take reactivity order of hydrogen hydrohaloacids, the priority is given to hydrogen iodide compound. HI is greater than HBr is greater than HCl compound. But most common used one is HI. So now ethers undergoes cleavage in the presence of hydrogen iodide or HX compounds. We have to apply the temperature nearly 300 above Kelvin temperatures. Then form the products. Here. Now ether is given ROR. So compound reacts with HI in the presence of temperature. Here. Ethyl cleavage is possible here. Nothing but carbon oxygen bond cleavage is possible according to our concept here. So here carbon oxygen bond undergoes cleavage means supposed to be oxygen electronegativity is more, means the bond electron migrate towards oxygen. Then oxygen act as a nucleophile. In this case. That means one type of nucleophilic substitution reactions here. Whenever primary, secondary is given, SN2 reactions, bimolecular nucleophilic substitution reactions, the connected carbon, the carbon connected with oxygen having tertiary nature undergoes unimolecular nucleophilic substitution reactions. Because already you know that conditions, what type of conditions are suitable for SN1 and SN2 reactions. These are the nucleophilic substitution reactions. So ethyl cleavage is possible. Carbon oxygen bond cleavage is possible here. So here RO minus means we need what here from H plus. Then ROH plus RI. One more alkyl iodide is formed in these reactions. Based on the given substrate reactant, we can write the products. For example, here CH3 is given, again CH2 is given, again CH3 is given. Ethyl methyl ether. Ethyl methyl ether undergoes cleavage with hydrogen iodide in the presence of temperature. Why? Because symmetric ether is given means directly we can write one convert into alcohol, another one convert into iodide. But wherever unsymmetric ether is given, unsymmetric means both alkyl groups are different here. Due to that reason, which one convert into alcohol, which one convert into iodide, we have to write that one here in this reaction. Based on the given ether connectivity, we can explain that concept. You remember always. So here CH3 again CH2OH plus methyl iodide is formed here. Methyl iodide. Always smaller alkyl group convert into iodide or alkyl halide compound. So how to form the product? We will see right now. If you write that mechanism, we'll get products here. So mechanism of this reaction. Here CH3 is given, again CH2 is given, again CH3 is given. CH3 is given. So Hi, H plus and I minus, Hi. So ether is carrying 2 lone pairs. Ether and oxygen is carrying how many lone pairs? 2 lone pairs. Ethers are generally called Lewis bases. Already we have discussed that concept. The lone pair migrates towards H plus, then form the bond here. Now here CH3 again CH2O again CH3 H plus here. Oxonium ion is formed here. Second step is the nucleophile attacking step. The nucleophile attacking step here. So incoming one is nucleophile. Always the incoming nucleophile prefer to choose less steric hindrance compound which is having small size. Why? Because steric hindrance is more, steric effect is more due to bulky nature. So that's why the nucleophile cannot attack this side because already bulky nature is there. Due to small atomic size, due to small size, due to molecular small size, the nucleophile can attack this side only. So if bulky nature is more, means steric effect is more, always incoming nucleophile choose less steric effect side. So the nucleophile attack that C. Attack that C here. Then form the CH3 again CH2OH. CH3 CH2OH plus methyl iodide. The bonded electron migrate towards oxygen, then form the neutral molecule. Due to the presence of positive charge, it accepts that bond pair. So smaller one convert into iodide, bulky alkyl group convert into alcohol in this reaction. You remember always incoming nucleophile attack that less steric hindrance side. The effect is generally called steric effect. The less steric effect is preferable to form the alkyl halide compound. Here iodide is given, alkyl iodide compound. Alkyl iodide compound. For example, here CH3 is given, again CH2 is given, O CH3. Ethyl methyl ether is given, here Hi compound. Hi compound here. Excess is given. Hi excess is given in the presence of temperature. So Hi excess is given in the presence of temperature 373 Kelvin temperature supposed to be. What will happen? In first step, smaller one convert into methyl iodide, bulkier one convert into alcohol. But excess is given, another mole of Hi if we take, then the alcoholic group OH group is substituted by iodide. Nothing but wherever X of Hi is given, then form the alkyl iodides. Alkyl iodides. So this is the way to write that products. Now CH3, CH2, OH plus CH3I. Again excess of HI, if you take another mole, the OH group is replaced by IEN. The OH group is replaced by IEN. This is the way to write that product. To write that product. Remember, excess of HI is given, excess of HBr is given, it converts into iodides or bromides or chlorides. Based on the hydrogen halide, we can write products in these reactions. Supposed to be here compound is given like this. Compound is given, OCS3 is given. OCS3 is given. Here HI is given. HI 373 Kelvin temperature. 373 Kelvin temperature. So ethanol oxygen undergoes cleavage in the presence of hydrogen iodide. It converts into iodide compound and phenol because steric hindrance is more, steric effect is more, and another reason, no chance to get the cleavage in between the carbon and oxygen because the given carbon is aromatic carbon, it cannot gain positive charge when you cleave the bond here. So no chance to cleave the bond in between the carbon and oxygen. So two ways we can explain in this reaction here. So your bond cleavage is possible. Phenoxide anion nothing but we require H plus. Methyl plus we require nucleophile here. Methyl plus we require nucleophile. So now if you take HI excess, your excess medium is given. If you take excess of hydrogen iodide, if you take excess of hydrogen iodide means the first step it convert into alcohol and methyl iodide. It convert into alcohol and methyl iodide, phenol and methyl iodide. If you take another mole, no chance to get the product. Why? Because given system is conjugated system, the single bond becomes to double bond. No chance to get the nucleophilic substitution wherever under normal conditions is given. So excess is given or one more HI is given. We have to stop that reaction at the stage of phenol and methyl iodide. Methyl iodide. If you want to get the nucleophilic substituted product means we have to apply the other conditions. Already we have discussed that concept in phenols. In phenols. Now, simple compound is given. We will write products like this. If connected carbon having different type of nature, secondary nature, tertiary nature. Because already I told you, wherever primary and secondary is given, only SN2 reaction is possible. Tertiary is given. How to write the product we will see right now here. Based on the tertiary nature, the molecule follows unimolecular reaction. For example, here tertiary butyl, methyl either is given. Here HI is given. HI is given. So 1 mole of HI is given in the presence of 373 Kelvin temperature. What type of cleavage is possible? Tertiary butyl oxygen cleavage or methyl oxygen cleavage. Wherever secondary primary is given, simple one undergoes cleavage. But here tertiary carbon is given, the molecule undergoes SN1 reaction. Nothing but cleavage is possible here. If you do cleavage in between the carbon and oxygen, we will get more stable carbocation. That means the reaction proceed via unimolecular nuclear. The reaction proceed via stable carbocation. Stable carbocation here. Stable carbocation. So stable carbocation intermediate. So C plus is formed here. We require what here from HI nucleophile because former one is electrophile. Then iodide attack that C plus, it convert into iodide plus here CH3OH. Again, one more of HI is given. The COH group will undergoes nucleophilic substitution, then form the methyl iodide compound here. That means here C again C again C I plus C I plus H2O. This is the way to write that products. Based on the connectivity of carbon, we can explain what type of cleavage is possible in ethers. Now, for example, here benzyl methyl ether is given. Benzyl methyl. What type of cleavage? Cleavage is possible in between the carbon and oxygen. Why? The reaction proceeds via stable carbocation intermediate. So now here CS2, benzyl carbocation is formed here. So that nucleophile attack that electrophile from the benzyl iodide. So smaller one converting to alcohol here. Smaller one converting to alcohol here. Again excess of HI is given. Excess of 1 mole HI is given. 1 mole HI means no chance to get the product here. So here CS2I and then plus Ci plus H2O. This is the way to write that products wherever ethers undergoes cleavage in the presence of HI and temperature. Supposed to be if we take cyclic ether. If we take cyclic ether, here HBr is given, HI is given 373 Kelvin temperature. Here excess of HBr are 2 moles. First step cleavage is possible in between the carbon and oxygen. That is left side or right side doesn't matter because both are having same type of connectivity, same type of nature. So one type of cyclic symmetric ether. So C plus means Br here, OH. OH means again excess is given, the OH minus is substituted by Br. This is the way to write that products wherever ethers reacts with hydrogen, halogen acids, halo acid compounds. Primary thing is connectivity is important to write the product in these reactions. Nothing but carbon, oxygen. Oxygen connected carbon has what type of connectivity? That one is very important in these reactions to write the products. Now, reaction with halogens. Reaction with halogens. The previous reaction is hydrogen iodide, hydrogen bromide or hydrogen chloride. That one is combination. Here, reaction with halogens. We have to write the product only depends on halogens. Ether compounds reacts with halogens like chlorine or bromine. Chlorine or bromine undergoes alkyl substitution here. Only alkyl hydrogens are replaced by given halogen. Nothing but chlorine or bromine here. It does not react with oxygen. Only one type of radical substitution reaction is possible here. So wherever 1 mole, 2 mole is given, alpha hydrogens are replaced by given halogen. Alpha hydrogens are mostly replaced by given halogen compound chlorine or bromine. Based on the connectivity, we can explain alpha carbon having how many hydrogens, beta carbon, gamma carbon like this, which is connected with oxygen is generally called alpha. So both are alpha carbons. Why? Because oxygen middle one here. Here one carbon, here one carbon. Both are alpha carbons. But based on the conditions, we can write products. What type of conditions? Dark conditions and light conditions. Dark condition is given only one hydrogen is replaced by halogen compounds. Wherever sunlight is given, all hydrogens are replaced by given halogen compounds. This is a way to write the products. Now, reaction with halogen compounds. Reaction with halogen compound, for example, here CH3 is given, here CH2, O, CH2 is given, again CH3 is given. The compound reacts with chlorine in the condition is dark condition. Condition is dark condition. According to structure, this one is alpha, this one is alpha. Next one is beta. Alpha connected carbon beta, beta connected carbon gamma, delta, like this. So only one mole of nothing but chlorine molecule, Cl2 molecule is given. Both are symmetric positions. One hydrogen is replaced by given halogen. One hydrogen is replaced by given halogen here, Cl, CH3. Alpha chloro. Alpha chloro. What is the position of chlorine? It is connected with alpha carbon. That's why it is called what? Alpha chloro. Alpha chloro. Diethyl ether. Diethyl ether. Diethyl ether. Supposed to be here. Again, ether is given. Dimethyl ether. Dimethyl ether is given. Reacts with 2 moles. Condition is dark condition, you remember. Condition is dark condition. One hydrogen is replaced by chlorine, another one is replaced by chlorine here because both are alpha connected carbons. Now, here CH3, that hydrogen is replaced by chlorine. O, that hydrogen is replaced by chlorine. O here, CH3. Alpha, 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 dichloro, alpha, alpha, dichloro, diethyl ether. Diethyl ether compound. Diethyl ether. This is the way to write the products. Alpha, alpha, dichloro ethers. Again, same diethyl ether is given. Diethyl ether, CH2, CH3. Condition here chlorine, sunlight is given. Or light is given, light condition is given. So light condition is given means light condition. So light condition, sunlight condition is given. All hydrogens are replaced by chlorine. Here how many hydrogens? 3 hydrogens. Here how many hydrogens? 2 hydrogens. Here 2 hydrogens, here 3 hydrogens. All hydrogens are replaced by chlorine. It is generally called parhaloether. Parhaloether or parhalodiethyl ether. Parhalodiethyl ether. How many moles we required here? 3 plus 2 5. 3 plus 2 5 means 10 moles of chlorine here. 10 moles of chlorine here. Here 2 moles HCl is formed by product. Here 1 mole HCl is formed. Here 10 moles of HCl is formed by product here. This is the way to write the products wherever chlorine or bromine react with ethers. Based on the conditions, we can write the products. Dark condition is given, we cannot make product this type of product, even having excess of chlorine here. Based on the conditions, we should write the product in this reactions. In this reaction. Now reaction with phosphorus pentachloride. Reaction with phosphorus pentachloride here. We can say that one type of preparation of alkyl halides. Here ether compound is given, ether ROR. The compound reacts with phosphorus pentachloride, then form the alkyl halogen compounds. How many alkyl groups? 2 alkyl groups. 2 alkyl groups means how many chlorines we required to get the alkyl halide? 2 chlorines. Then 2 R groups, and we required 2 chlorines. 2 moles of alkyl chloride is formed in this reaction. Remaining how many phosphorus atoms? 1. Remaining how many oxygen atoms? 1 here. Remaining how many chlorines? Total number of chlorines 5 here. How many used in this reaction? 2. Then remaining chlorines are 3 here. Phosphorus oxide trichloride is formed here. For example, here C2H5O, C2H5 is given. Diethyl ether compound reacts with phosphorus pentachloride, then form the 2 moles of ethyl chloride. How many moles? 2 moles. 2 moles of ethyl chloride. Remaining oxygen, phosphorus, chlorines, then form the phosphorus oxide trichloride. This is the way to write the products wherever ether reacts with the phosphorus pentachloride. Reaction with acid chlorides. Reaction with acid chlorides. When ethers heated with acid chlorides in the presence of anhydrous zinc chloride or AlCl3 form the alkyl chlorides and ester compounds. Acid chlorides or C11OCl. Whatever organic molecule is given, if the organic molecules are carrying or C11OCl is called acid chlorides. That acid chloride reacts with ether, heated with ether in the presence of temperature and anhydrous ZnCl2. It converts into alkyl halide and ester compounds. Now we will see right now here. Here acid chloride is given, or C11OCl plus ROR ether is given. ROR ether. Anhydrous ZnCl2. Anhydrous ZnCl2 is given. What will happen here? So R here C11OR plus R C11OR plus R C11OR plus RCl. Alkyl halide and the compound is formed. This is the way to write that, because acyl cleavage is possible here. Acyl cleavage. For example, here C2H5, sorry. CH3C11OCl, acyl chloride compound. CH3C11OCl, acyl chloride compound reacts with dimethyl ether in the presence of anhydrous ZnCl2. Form the CH3C11OCH3 plus CH3Cl. Methyl chloride is formed here. Methyl acetate is formed here. This is the way to form the products wherever ethers reacts with acid chlorides. In the same way, we can write the product wherever ethers react with the anhydrates. So for example here CH3 is given flow, here CH3 is given anhydride, CH3 acetic anhydride is given, CH3 C double bond O CH3. Here bond cleavage is possible means CH3 C double bond O plus. We require what here plus means minus. So now here CH3 again C double bond O plus O minus again CH3 plus O minus. Here CH3 C double bond O minus. We require what plus here CH3. Nothing but 2 moles of ester is formed here. 2 moles of ester is formed here. So reaction with acid anhydrides. Reaction with anhydrides. So in the presence of ether heat, when ether heated with anhydride, in the presence of anhydride ZnCl2 form the 2 moles of ester. 2 moles of ester. This is the way to write the product whenever ether reacts with acid chlorides or anhydrides. Acid chloride is given, 1 mole convert into halide, 1 mole convert into ester. Anhydride is given, form the 2 moles of ester. But whatever compound is given doesn't matter. Based on the connectivity of carbons, we can write the product in these reactions also. This is the way to write the product with acid chlorides and anhydrides. So thank you. Remaining properties we will see in session 38.